Some of them stopped existing because of saddle nodes, and you see some saddle nodes here. You see one here. You see one here. Here you see a pitchfork. You see that this state emerges from this branch. Here you see a bunch of pitchforks from the zero state, meaning from the conductive state. Here you see another saddle node. Here you see another saddle node. This is, okay, I shouldn't have written this. This is not a complete bifurcation diagram. There are many more branches than this. Hence, what I said to you yesterday, wasn't it yesterday that we had a transition class? I said there are many, many unstable steady states for Navier-Stokes for plane co-ed flow, and some people think that explains turbulence, but I say no. Here is something that's at least as complicated as what they found for plane co-ed flow, but this system does not exhibit any turbulence. These pictures are nice, but when you're in one of those states, you just stay there. You don't go from one to the other. This is not turbulent at all. It's just there are simultaneous stable steady states. And if you count the unstable states, well, there's a zillion. And this is just a property of nonlinear equations, of Navier-Stokes, of Boussinesq, of all those. It's not strange. It's normal. It's the norm. That's not, okay, the critical Reynolds number here is 1800. Before that, there's only one branch, only the conductive branch. That's the first one to bifurcate. But then after that, there's all kinds of things that happen. If you go to sufficiently low Reynolds number or Rayleigh number, the solution is unique. And you recall that from the class 3 or class, and therefore it respects the symmetry, meaning it is flat, it has no, you can't distinguish one point on the cylinder, on the one azimuthal point from another one. Okay, we can zoom in on different parts of this picture. Here we are, we can zoom in on the branches that are created here. Not all of them are. Some of them are created all by themselves up here, but some of them are created as bifurcations from zero. And here they are. Remember I showed you, I think it was it yesterday, the day before? Successive pitchfork bifurcations. Each one here has a different symmetry. Before we talked about them having different wave numbers, and here they do have different wave numbers, but these are azimuthal wave numbers in theta. This is m equal 1, dipole. This is m equal 2. This is m equals 0, axisymmetric. This is m equal 3. These are successive bifurcations. Again, many things that we've mentioned over these past week and a half. This one is going to be born stable, but these others will be born unstable necessarily because their parent at the moment of bifurcation was unstable. This one's stable, the other ones will be born unstable. Things might happen that may stabilize them, but at the bifurcation you can be sure right above their creation they're unstable. We can look at, okay, this diagram is really hard to understand. We can separate, okay, breaking of symmetry is something that happens at a bifurcation, and things of the same symmetry kind of clump together. You cannot go from one symmetry to a whole nother symmetry. I alluded to this a little bit. If you go to something that's less symmetric in a bifurcation, that new symmetry, it's a subset of the old one. Okay? You're not going to have a bifurcation that brings you, say, from m equal 2 to m equal 2. That's not possible. This is not a subset of that. You can go from m equal 3 to m equal 6. You can go from m equal 2 to m equal 4, but you can't just go from this to this. They're not compatible with one another. So that means that we can actually separate out the bifurcation diagram here into those that have different symmetries. We can take the ones that came out of the m equal 2, and we can put them all together, and that's what's done here. This is the pizza branch. And we notice back here, was there anything that looked like pizza? No, there wasn't. So let's think a little bit about why that is. Here's the pizza branch, and it's born unstable, as I said it had to be. That's what that thin line means. And then you continue, and it stabilizes an eigenvalue that was positive crosses and becomes negative. And now it's stable for this tiny little interval here. So we do see some pizza, and I think that's shown here in this picture here. Where's this pizza? Yeah, pizza over a very tiny interval. It was some pizza. But it wasn't in the regime where they did. And then this branch undergoes another bifurcation, a symmetry breaking bifurcation. I'll tell you about that in just a moment. And you continue it, and this is stable, and it evolves like this into eventually being a 4-roll state. And the 4-roll state was actually seen, that's a nice robust one, that was seen at one of the experimental parameters. It looks like this. It's got two white places here, like this. Let's see if we can see something that looks like that. Yeah, it's like this. This is a 4-roll state. 1, 2, 3, 4 rolls. They're in a cylinder, so they don't look like rolls, but this is it. And that arose from the bifurcation to the pizza. Again, let's go back and discuss some of what we said here. I said this was a symmetry breaking bifurcation. This is a pitchfork of some kind. I went this way, but there's also a branch that I didn't draw that's missing. There are lots of branches here that I didn't draw that are missing. For example, here, this is what kind of bifurcation? What kind of bifurcation is this? This you should know from the 3rd class. This is a sorry? This is a
Subcritical?
nope, it's not that it's not.
Is it the exchange of stability?
Nope. Now, from what we said to you, okay, I'm going to say that I think we know that it's not subcritical. I was going to say that we don't have any means for telling it, but what made you say it was subcritical?
That it's unstable.
It's unstable, but it's born of an unstable parent. So that's not, the parents, the children and bifurcation resemble the parents. So the question here about its being subcritical or supercritical would be decided by which way the eigenvalue was changing, and whether this was more stable or less. Okay, this has the same stability as this, yes, but the question would be, but both are unstable, as I said. The question is this branch more or less stable than that one? And that we don't know, but everybody's unstable here. Okay. Anyway, not subcritical. And exchange of stabilities is not a word that I recognize. All bifurcations change stability. Some people use exchange of stabilities as a synonym for transcritical, I think, or some other people use it as a synonym for steady bifurcation, as opposed to Hopf. But I think it's a vague word that means a lot of different things. More guesses, please. You're going to make me feel bad. I've been here for a week and a half, and none of you know this basic lesson. At least 2 people volunteered to answer, even if they were wrong. Come on, somebody else. Let's go. You know. Tell me. Yes, you.
No.
No? You know. No?
No.
You know. No? You know.
How about bifurcation?
Nope, there's no motion. No motion here.
No motion.
Everything's steady. It's a circle pitchfork. It's a circle pitchfork. It could have any phase. Oops, I thought this would happen someday. It can be, it has this orientation. It could have this one or this one or this one or this one. There's O2 symmetry around this circle. You've broken the O2 symmetry. You've chosen an axis. 4 axes, as it turns out. It could have any phase. This is a circle pitchfork. Okay, there's 2 pi's worth of solutions there. A circle's worth of solutions. You can rotate that one. Okay. You've broken symmetry, meaning that now, after the bifurcation, before you had a flat surface, and afterwards now you have you have a selected axes, but those axes could have been in any direction. Okay, so that's what's happening here. You have a circle pitchfork, and that you create, this new thing has symmetry D4. D4 or D2? D2, no, D4, there. No, D2. D2.
Have two rotations
Yeah.
and two reflections.
Excuse me?
It's two rotations and two reflections.
That's right, so it's D2. It's D2. And so this has D2. Now, when you do this, okay, you can see this has a certain kind of symmetry in that. Don't worry, I'll go back to numerics. Oh, he left. I will. I'll do more numerics in just a moment. This certainly has a lot of symmetry. You can see that, of course, there's the D2, but in addition, not only is there the D2 tells you can do a rotation by pi, right? But also you have more symmetry than that, because if you rotate by pi over 2 and turn purple into yellow, you get the same state. And now, when we bifurcate here, we've broken that symmetry. We see that purple and yellow are not equivalent. There's purple down the center and yellow on the sides, and you can't say that about yellow. Here, anything you could say about purple, you could say about yellow as well. Here you have broken that symmetry. This has less symmetry than this. This is definitely a purple in the center sort of state. Of course, there exists, it's a pitchfork, there exists another solution in which there's a yellow in the middle and purple on the sides. A different one. Okay. So this is a circle pitchfork, and this is a regular pitchfork that's distinguished between the purple and the yellow. And finally, at the end, you create 4 rolls, and that one is the one that's observed in the experiment. So that you would never think that. You know, the fact that this is the final result from here, it doesn't look at all like that. But that's what it's like. And it's got to be, because there's a result that says that, okay, you recall we said that linear equations, linear constant coefficients equations, their solutions are exponentials. We said that any number of times. And by exponential, I include trigonometric. Why do we always write e to the sigma t for our time dependence when we have bifurcations? You know, because we have an exponential. But so too, this is constant coefficient, this is homogeneous in theta, meaning no theta is special, meaning that the solutions are exponentials in theta. And of course, they can't be exponentials in theta. By exponentials, we mean trigonometrics in theta. This is a linear problem, it's a linear stability problem, and hence, the solutions must all be trigonometric. Nothing can bifurcate from this that looks like 4 rolls. It has to be something that looks like this. It has to be trigonometric if it's going to bifurcate from the conductive state. For the very same reason that you know so well that if you write x double dot plus bx dot plus cx equals 0, that the solution is e to the lambda t. You know that. And that same principle tells you that here the solutions are e to the I m theta. And hence, this thing here could not possibly have bifurcated from the conductive state. These and these can, and these, but not this, and not this, and not this, and not this. They must be disconnected just by looking at them, without even doing any calculations. Okay, so naturally I could talk about this all day, but I should probably get back to some numerics. Now let me do a little bit more. The m equals 0, you notice that over here there were tori. Here's an axisymmetric solution here, and here's an axisymmetric solution, and here's another one with 2 tori, and it turns out that the bifurcation diagram for that looks like this. It's very complicated. You might think, once you did this, oh, I found that m equals 0. Now I know where the axisymmetric solutions come from. But no, it turns out that in this problem, some of them come from that. This bifurcation, this is schematic. It doesn't really have this kind of dependence. Here you're stable from here to here. Remember, these are born unstable. But there's a whole bunch of other ones here. These are also axisymmetric, and they're born from no place. They come from a saddle node bifurcation. It's just how it turns out. I'm not saying there's anything universal about this, or just to say bifurcation theory in action here. And the prettiest one here comes from the Mercedes. You remember the Mercedes that's here. That's what was observed. But as we said, this is not a trigonometric pattern. This is not n equal 3. It can't be. A trigonometric pattern has yellow and purple having the same status. You know, when you do sine theta, you have plus, minus, plus, minus, plus, minus. You don't have some big plus, little minus, big plus, little minus. You know the pluses and the minus look the same. It's kind of smoothly varying.